All right, let's talk about algebra. Just hearing that word probably brings back some memories, right? For a lot of us, it was late nights, staring at problems, and wondering what on earth x was supposed to be. It's really that first time math goes from concrete numbers to this abstract world of symbols and patterns.
So, why is it that so many of us hit a wall with algebra? Well, it's a completely different way of thinking. You're suddenly asked to stop just crunching numbers and start seeing the logic and the relationships behind them. It's like learning a whole new language, and honestly, a lot of students feel like they've been thrown in the deep end.
But here's the deal. Cracking that code is, it's pretty much non-negotiable. Getting a handle on algebra isn't just about passing one class. It's the key that unlocks the door to higher math, to college, and to so many careers in science, tech, engineering, you name it. The stakes are really, really high. Okay, so if it's that important, how do we get better at teaching it? Well, the great news is we don't have to guess. Researchers have been digging into this exact question for years, searching for proven, evidence-based practices that actually make a difference in the classroom.
And for this explainer, we're diving into a really fantastic practice guide from the Institute of Education Sciences, or IES. These folks did the heavy lifting. They combed through tons of studies to pull together the absolute best, most effective strategies for teaching algebra. They've basically given us a playbook for what the research says works.
So here's our game plan. We've talked a bit about the problem. Now we're going to break down 3 powerful strategies right from that guide, using solved problems, learning to see structure, and exploring different paths to an answer. And then we'll wrap it all up with the bigger picture. These are the 3 big ones, the core recommendations from the IES guide. And what you'll see is that each one is really about shifting the focus, moving away from just finding the answer and toward deeply understanding the why and the how. So let's jump in. All right, strategy number 1 is all about using solved problems. Now, think about it. Algebra forces your brain to juggle a lot of abstract concepts at once. It's a huge cognitive load, as researchers call it. But when you study a problem that's already worked out, you can see the entire logical journey from start to finish. It can make learning way more efficient. So what exactly do we mean by a solved problem? It's simple, really. The guide calls it an example that shows you both the problem and all the steps taken to get to the solution. You get to see the whole path laid out right in front of you. And this is where it gets really powerful. The research shows that one of the best ways to use these is to compare a correct answer with an incorrect one. So on the left, you see the right way to factor this expression, but look at the right. That's a super common mistake. The student found factors that multiply to -24, sure, but they forgot that those factors also have to add up to -10. Putting them side by side like this lets a student see the exact point where the thinking went off track. It's an amazing learning moment.
And this is the kind of thinking this whole strategy is meant to spark. The goal isn't just to robotically follow the steps. It's to ask these deeper questions about how the pieces of the puzzle fit together, to really analyze the problem's structure, which, hey, brings us right to our second strategy.
Let's move on to strategy 2, which is all about learning to see structure. You can think of this as understanding the grammar of math. It's being able to recognize that 2 problems might look totally different on the surface, but underneath, they share the same mathematical DNA. The guide defines structure as those underlying mathematical features and relationships. You know, where the variables are, what the operations are doing, and how simple ideas are nested inside more complicated ones. It's the blueprint of the problem. And a huge part of seeing that structure comes down to using precise language. For example, saying, "the numbers cancel out," is vague. Do they add to 0? Do they divide to 1? It's much clearer to say they add to 0. Saying substitute 2 for x is so much more precise than just plug in the 2. This isn't just about being nitpicky. Using precise words forces our brains to see the exact mathematical action that's happening. And here is a perfect example of why that matters. So you're looking at different equations for the path of a thrown horseshoe. They all describe the same path. But this one specific form, the vertex form, is special. It makes one part of the structure pop right out at you, the maximum height the horseshoe will reach. Changing the form can reveal totally different insights. This brings us right to our third and final strategy, teaching students to find alternative paths. The idea here is to help them build a flexible problem-solving toolbox, and to get them to see that there's almost always more than one way to get to the right answer. Now check this out. This slide shows this idea in action perfectly. Look at Devon's strategy. It's a standard, totally valid approach. Distribute everything first. It works great. But then look at Elena. She noticed the structure of the problem. She saw that y+2 term on both sides and treated it like a single chunk. By subtracting 6 times y+2 from both sides, she solved the problem in just 3 steps. It's not just correct, it's elegant and efficient. And this is what that problem-solving toolbox looks like in practice. When a student is faced with a quadratic equation, they don't just have one memorized procedure. They have a whole menu of options. They can try factoring, they can graph it, they can complete the square. The goal isn't to master every single tool, but to have the wisdom to pick the right one for the job at hand. So let's pull all this together. These 3 strategies, using solved problems, seeing structure, and finding alternative paths, they're more than just neat tricks to use in the classroom. They really represent a fundamental shift in how we think about teaching math. Because when you look at them all together, you see these common threads. They're all about developing a deep conceptual understanding, not a shallow one. They're about valuing the process, not just the final answer. And they're about encouraging precise communication so that process is crystal clear. It's really a shift from asking, what's the answer, to asking, why does this work?
And that really leaves us with one last big idea to chew on. What if we reframed the entire goal? What if math class wasn't just about finding the right answer? What if it was about learning how to think, how to be more flexible, more logical, and more creative in our problem solving? Now that is the real power of cracking